Imagine stepping into a world where dragonflies were the size of hawks, millipedes stretched longer than a car, and the air itself seemed built for monsters. This was not science fiction. Around 300 million years ago, during the Carboniferous Period, Earth became a strange green empire of endless swamps, towering forests, and giant bugs that would make modern insects look like toys. But this was more than a prehistoric horror show. It was a turning point in the history of life, when the planet was experimenting on a grand scale. And somehow, for a while, insects became some of the most astonishing rulers Earth had ever seen. To understand why giant insects appeared, we have to visit a version of Earth that looked wildly different from today. The Carboniferous Period, roughly 359 to 299 million years ago, was a planet of wet lowlands, steamy air, and immense forests packed with giant club mosses, horsetails, and early ferns. There were no birds singing from the trees, no grass underfoot, and certainly no humans complaining about mosquitoes. Instead, vast swampy ecosystems stretched across the continents, and dead plant matter piled up faster than it could fully decay. Over time, much of that buried vegetation would become the coal deposits that later gave the Carboniferous its name. In other words, this age was not only the era of giant bugs, it also helped stock Earth's future fuel tank. These forests were not quiet, peaceful postcard forests either. They were dense, humid, and alien. Tree trunks rose like green pillars, but many were not true trees in the modern sense. Some of the dominant plants reproduced with spores instead of seeds, and their strange architectures made the landscape look almost like another planet wearing a plant costume. The ground was soaked, the air was warm, and oxygen levels were unusually high. That last detail matters more than almost anything else in this story, because it may explain why insects in this period could grow to such absurd sizes. Unlike mammals, insects do not breathe with lungs. They use a network of tiny tubes called trachea that carry oxygen through their bodies. This system works well for small creatures, but it places limits on how large they can become. If an insect becomes too big, oxygen has a harder time reaching deep tissues quickly enough. But during parts of the Carboniferous, atmospheric oxygen may have climbed far above modern levels. Today, oxygen makes up about 21% of the atmosphere. Back then, it may have reached roughly 30% or even more. For insects, that was like upgrading from a bicycle pump to an industrial air compressor. With more oxygen available, these animals could support larger bodies than their modern descendants. That is how Earth ended up with creatures like Meganeura, often described as a giant dragonfly-like insect with a wingspan of around 2 feet. Picture a flying insect the size of a seagull cruising over a swamp, scanning for prey. Suddenly, your average housefly no longer seems like such a personal insult. Then there was Arthropleura, a massive, many-legged arthropod that could grow over 8 feet long. It probably did not hunt humans, which is comforting only if you are willing to ignore the fact that it looked like a nightmare assembled from armor plates and too many legs. But giant size was only one piece of the Carboniferous story. This was also an age when terrestrial ecosystems were becoming more complex and ambitious. Life had already moved onto land earlier, but now forests were expanding dramatically, soils were deepening, and food webs were becoming richer. Insects were among the great winners of this transformation. They could fly, crawl, burrow, climb, and exploit new plant-rich habitats in ways many other animals could not. They were adaptable, fast-breeding, and surprisingly innovative. In a world where vertebrates on land were still relatively modest, insects had room to become the strange overachievers of the age. And vertebrates really were still figuring things out. Amphibians were common in these wet environments, and early reptiles were beginning to appear, bringing with them a major evolutionary breakthrough: eggs that could survive away from water. That innovation would eventually reshape life on land. But during much of the Carboniferous, the stage still felt open enough for arthropods to dominate many everyday scenes. If you stood beside a swamp pool at dusk, you might see giant insects buzzing overhead, armored arthropods moving through leaf litter, and primitive tetrapods lurking nearby like nervous newcomers in a world already claimed by bugs. What makes the Carboniferous so fascinating is that it was not just weird for the sake of being weird. It was a planet in transition. Forests were changing the atmosphere. The atmosphere was changing animal possibilities. And those new possibilities produced creatures so bizarre that they still feel half mythical today. The giant insects were not random monsters dropped into the timeline for entertainment. They were the logical result of a very specific world with very specific rules. Earth, in this period, was running an experiment. And for a while, the answer it came up with was simple, outrageous, and unforgettable. Make the bugs bigger. And yet, the deeper surprise of the Carboniferous is that giant insects were not simply oversized versions of the bugs we know today. They belonged to ecosystems that operated by rules almost unfamiliar to the modern eye. This was a world before flowers, before birds, before grazing mammals, before the elegant balance of modern forests. Even the soundscape would have been strange. No birdsong, no buzzing bees hopping from blossom to blossom. Instead, the air may have been filled with the rustle of spore-producing plants, the flap of giant wings, and the wet, swampy soundtrack of a planet still inventing what life on land could become. Take Meganeura, for example. It is often casually called a giant dragonfly. But it was not exactly a dragonfly in the modern sense. It belonged to an ancient lineage related to them, but not identical. That detail matters because the Carboniferous was full of evolutionary experiments. Creatures that look familiar at first glance and then become wonderfully strange once you inspect them closely. Nature was sketching early drafts. Some designs would lead to modern lineages. Others would vanish, leaving only fossils and the eerie feeling that Earth once tried out a completely different cast of characters. The same is true for the forests themselves. These swamps were not just scenic backdrops for giant bugs. They were active biological engines. Plants were pulling carbon dioxide from the atmosphere in enormous quantities, locking carbon away in buried organic matter, and helping reshape global chemistry. In a sense, the forests were hacking the planet. Their explosive growth may have contributed to higher oxygen levels, cooler climates in some intervals, and even major shifts in Earth's carbon cycle. So when we picture giant insects ruling this world, we should not imagine them in isolation. They were part of a much larger environmental revolution, one in which plants, atmosphere, climate, and animal evolution were all tangled together like roots in a drowned forest. Then there is the question every modern viewer quietly asks: why did these giants disappear? Why do we not have dragonflies the size of drones patrolling parks today? The answer seems to be a mix of changing atmosphere, changing ecosystems, and changing competition. As oxygen levels later dropped, the built-in respiratory advantage that helped support enormous arthropods likely faded. At the same time, vertebrates became more formidable. Reptiles diversified, ecosystems shifted, and life on land grew more competitive and more dangerous for giant arthropods trying to stay on top. It is hard to be the ruler of the planet forever when the planet keeps rewriting the rules. There is also a hidden twist here that makes the Carboniferous even more fascinating. Giant size was not necessarily a guarantee of invincibility. Bigger bodies can offer advantages, but they also come with costs. Large insects would have required more resources, more stable conditions, and efficient movement in habitats that could easily change. If oxygen dropped or environments fragmented, being enormous might stop looking like a superpower and start looking like an expensive lifestyle choice. Evolution is not sentimental. It does not preserve creatures because they are impressive. It preserves what works now. And the fossils themselves tell a story that is both dramatic and incomplete. Insects are delicate animals, and fossilizing them well is not easy. That means every wing impression, every body segment, every trackway is like a postcard from a world that usually refuses to leave mail. Some scientists have even studied fossil footprints and trace fossils to reconstruct how these creatures moved, where they lived, and how the forests were structured around them. So the Carboniferous is not just a parade of monsters. It is a detective story written in stone, coal seams, and ancient mud. Perhaps the most astonishing part is that this age of giant insects was not a weird side note in Earth history. It was a major chapter in the construction of the modern world. The coal that powered factories millions of years later began as Carboniferous plant matter. The rise of complex terrestrial ecosystems accelerated here. The contest between atmosphere and anatomy, environment and evolution, played out here with almost theatrical boldness. Giant insects were not just oddities. They were evidence of how flexible life can be when conditions change. That is what makes the Carboniferous feel so modern in spirit, even though it looks utterly alien. It reminds us that Earth is not fixed. It can create worlds so strange that they seem impossible, then erase them so thoroughly that their existence feels like a rumor. One era grows giant dragonfly-like predators and armored arthropods the size of furniture. Another gives rise to dinosaurs. Another produces humans in shoes, staring at fossils and nervously deciding that maybe today's insects are already big enough. So why does the Carboniferous matter beyond the sheer entertainment value of giant bugs and prehistoric nightmare fuel? Because it reveals one of the most important truths in Earth's history: life does not evolve in isolation. Change the atmosphere, and you change what bodies are possible. Change the forests, and you change the chemistry of the planet. Change the chemistry, and suddenly evolution begins writing in a completely new style. The Carboniferous was not just an age of strange creatures. It was an age when Earth itself became a co-author of biological invention. It also reminds us that the world we think of as normal is only one version of reality among many. Today, we are used to birds owning the skies, mammals dominating the land, and insects staying mostly within the size range of annoying rather than small helicopter. But normal is temporary. For millions of years, another version of Earth existed, one where swamp forests spread across continents, oxygen ran unusually high, and arthropods expanded into forms that now seem almost absurd. If you had been alive then, you would not have called it bizarre. You would have called it home. There is something humbling in that. Humans often imagine Earth as a stable stage with a few costume changes. In truth, it is more like a theater that keeps tearing down the set, rewriting the script, and casting entirely new stars. The Carboniferous proves that even the most basic-looking rules of the living world can shift. Size limits change. Winners change. Whole ecosystems appear, flourish, and vanish. What feels permanent is often just the current episode, and that perspective matters today more than ever. When scientists study ancient climates, atmospheric chemistry, extinction patterns, and ecosystem change, the Carboniferous offers a deep-time laboratory. It shows how tightly connected life and environment really are. Forests did not merely decorate the planet, they transformed it. Oxygen did not merely fill the air, it shaped anatomy, behavior, and ecological power. The past is not dead data. It is a manual written in fossils, showing us how Earth systems respond when major variables shift. Of course, there's also the pure wonder of it all. Few chapters in natural history hit the imagination quite like this one. A giant dragonfly-like predator gliding over black water swamps. An enormous millipede relative moving through dense prehistoric undergrowth. Amphibians lurking like half-finished experiments. Forests so alien they seemed designed by a civilization that had heard of trees only through rumors. The Carboniferous feels like fantasy, yet it was entirely real. And that is often where science becomes most powerful. Not when it makes the world smaller and neater, but when it makes reality feel bigger, stranger, and more astonishing than fiction. In the end, the giant insects were not the point. They were the signal. They told us that the planet was operating under a different set of possibilities. They were living proof that when Earth changes, life can answer with forms beyond ordinary imagination. The Carboniferous was a time of bold experiments, planetary chemistry, buried forests, and evolutionary ambition on a grand scale. It was the age when bugs became giants, but also the age when Earth showed just how radically creative it could be. And maybe that is the image worth carrying with us. Not just a monstrous insect in a swamp, but a world still inventing itself. A world where the air was richer, the forests deeper, and the boundaries of life far wider than they seem today. The Carboniferous is gone, but its lesson remains. This planet has always been more imaginative than we are. Sometimes all it takes is one fossil wing and stone to remind us.